So I may have already shared with you that I find concept mapping a really valuable study method, but when I in particular, I don't know if I'd say fell in love with it, but saw its utility was actually in organic chemistry. And that's because all of the organic families and reactions do start to kind of get convoluted because they're all related. And it was really hard then for my brain to try to keep them straight. And so I think a really valuable tool for that is concept mapping, developing intentional concept maps to help you see the relationships. There's a lot of science on why this is good for your brain because it's kind of in a way the way our brain works. One thought triggers another and another and another. So the more connections you can see, the stronger the memory map in your brain. So let me show you what that might look like, and I'm going to walk you through some ideas. So I'm going to start by just writing some organic families that we've covered so far. I might not get all of them, but just some that I want to focus on. So we've covered alkanes, so I'm going to put that on there. We've covered, let's see, alkenes and alkynes too. I'm going to probably focus on the alkenes a little bit more, but alkenes and alkynes. We've covered alcohols. We've covered ethers now, and we've also covered aldehydes and ketones, which are related but just a little bit different. Aldehydes and ketones. Okay, so and you could add more. You could have all of the every single one we've covered so far. I just thought for space and stuff, I might just do this one. So once you've identified the things that you want to concept map, you can immediately jump into looking at relationships between them. But what I'm going to do is I'm actually going to switch gears, and I'm going to just do their general formulas. I'm going to add some notes to them. So the general formula of alcohols, for example, is R group with an OH. Alkenes, carbon double bonded to a carbon. Carbon double bonded, triple bonded to a carbon for that. Ethers, here's our general formula, because we want to, it's really important that we recognize the general formulas really well. For our aldehydes, carbonyl, hydrogen, R, ketone, really similar, but R and R, where both R's have to be carbons. So sometimes I'll actually do carbons. They have to be carbons, whereas this could be a hydrogen or a carbon and still be an aldehyde, but these have to be carbons. And then alkanes, of course, their general formula is this, maybe R. These are other carbons, so there isn't really a general formula of an alkane. Another thing you could do with your concept mapping is compare some properties. So one thing you might want to consider if you're watching this video is to develop your own concept map, and then watch what I do and see either how they might compare, how we developed relationships differently. So I'm going to jump into properties a little bit. So alkanes, for example, are saturated, so only single bonds. Alkenes are specifically unsaturated. So I'm just getting some properties off of them. And then alcohols, ethers, aldehydes, and ketones can be kind of a mix, though obviously these can't be fully saturated. So we have some degree of unsaturation in there as well. Alkanes are nonpolar, right? Alkenes and alkynes, assuming they're hydrocarbons, are nonpolar as well. If they're substituted with something else, they might not be, but nonpolar. Whereas our alcohols are they're polar, very polar. We'll say very polar, to the point that we actually have hydrogen bonding between them. And the reason that's important maybe to note in comparing these is that if I'm asked to compare across family groups for something like boiling point, I want to use this information. I would expect an alcohol to have a higher boiling point than an alkene, alkyne, or alkane, assuming they're relatively similar molecular weight because of this hydrogen bonding. Now, ethers are kind of polar. I mean, they're a little bit polar, but it's not very significant. So I'm going to say low polarity. Low polarity. Because that's going to affect a little bit that idea of boiling and melting point, but also solubility. you know, so they have a little bit polar, water can hydrogen bond with them. I could include solubility information, you know, nonpolar, therefore not soluble in water, you know, not soluble in water, soluble in water. Let's go ahead and do that. Not soluble, not soluble, soluble. Now that's, of course, going to depend on the size of the R group. So soluble, but I'm going to say depends on R, and also, you know, the number of these. So it's you know, so low polarity, water can hydrogen bond to it though. So we'll say low solubility for the smaller ones. So somewhat soluble depending on the R group, low solubility, low soluble depending on R group. And then here we have, I would say they're mildly, a little bit more mildly polar. So again, soluble in water as long as that R group is small. So small ones equal soluble. So we're comparing, because again, these are the kinds of questions you get, is asking you to compare across these families. So we could probably add some other properties as well. Now, one of the places I think we really want to focus our attention is reactions, especially reactions between. So for example, we have learned that you can take an alkene or an alkyne and you can turn it into an alkane. So this green reaction is showing that it can be turned into an alkane. So I want to include some details on that type of reaction. So an alkene or an alkyne can undergo, it can be turned into an alkane through hydrogenation. Right? So that means to add hydrogen gas to. And because as I'm thinking this, I'm like, I want to include the details that I might want to note or study. So can be, and that's, you know, metal catalyst, or I put platinum, but you know, you could just say metal catalyst. So hydrogenation, you can hydrogenate an alkene or alkyne to an alkane. You can also take an alkene and turn it into an alcohol. So we see the relationship between these. And what's that reaction type called? So that's a hydration reaction. And I want you to note this is specifically going to the alkenes and not the alkynes. So a hydration reaction. So a hydration reaction means we add water, and that's usually done in the presence of an acidic catalyst and some degree of heat depending on the alcohol that we want or the type of alkene. So we have a way to go from an alkene to an alcohol. Now, we're going to start to see our thing getting kind of fun and complicated, and this is I think beneficial because it helps our brain see the relationship. An alcohol can be turned into an alkene. So an alcohol you can lose that OH group and close that bridge into a double bond, and that it's an opposite reaction of this. So it is a dehydration reaction. Dehydration. So we can dehydrate an alcohol to an alkene. So what that ends up looking like is our alcohol is on this side, and then over here we get water and then our alkene. I'm going to just say ene. And it also, just like this one down here, water, or acidic catalyst and heat. So see how these are almost exact opposites of each other. So an alcohol can also be turned into an ether. What's that reaction like? So an ether, especially these symmetrical ethers, can be built from this portion. So notice how this OR, through the condensation reaction. Through a condensation reaction. So in this kind of reaction, we're going to have we'll do it up here. We're going to have two alcohols and acidic catalyst and heat. You're starting to see some, I see that 3 times. It doesn't mean it's always the catalyst, like here it's platinum or some type of metal catalyst, but we get two alcohols that react together to give us the water, and then because they're going to be, one's going to lose an OH, one is going to lose an H, and we're going to get an ether from that. So is there a relationship here as well between any of these others? Yes. Aldehydes and ketones can be used to make an alcohol, can react to make an alcohol. And that is through a very similar reaction to here. It actually occurs in almost the same way as hydrogenating the alkene. So when we hydrogenate the alkene, we open up the double bond, you know, jazz hand, and now we have a single bond between them. And one jazz hand grabs the one hydrogen and one jazz hand grabs the other, and that's how we end up with the alkane. Same thing here, except rather than a carbon bonded to a carbon, we have a carbon bonded to an oxygen. So we lose the double bond, jazz hand. These are my jazz hands, pretty fancy, huh? One of them grabs a hydrogen and the other grabs a hydrogen. So I want you to see the similarity here. Do you see it? Like what's happening is really the same at the atomic level, but since one is an oxygen, already we end with an alcohol instead of an alkane. So we can turn an aldehyde or a ketone into an alcohol through hydrogenation. And again, that's going to occur the exact same way. So let's go ahead. Plus a hydrogen, metal catalyst. And a lot of times, once you find that you can go one way, you can go the other. So an alcohol can be turned into an aldehyde or ketone. An aldehyde or ketone. And that is through the process of oxidation. When we oxidize, so we'll see this in our chemical formula, or maybe we'll see something like the potassium dichromate or sodium permanganate or something like that. So dichromate or dichromate or permanganate. So those are, we might see this in the reaction. And so we, lose a water molecule from within the alcohol, and we get a double bond forming right here. We lose this hydrogen, we lose a hydrogen that's off the R group, and this double bond closes it up. So this happens through oxidation. Now only primary and secondary can do that. The tertiary cannot be oxidized to an aldehyde or ketone. So we'll do not tertiary. Now, aldehydes and ketones can both be hydrogenated, but you're only going to get a primary or a secondary. If it's an aldehyde, you're going to get a primary, so we'll do that on that path. And if it's a ketone, you're going to get a secondary. Not able to get a tertiary alcohol through the hydrogenation process. So obviously this is a very complex picture at this point, but the truth is, the things we're studying are complex and interrelated. Now, this is not the only concept map we could have generated, and you might have generated a better one or a different one, but I would encourage you to use concept mapping to help your brain sort out. You could do a concept map that focused more on naming than on physical properties or chemical relationships. You could do a concept map that included phenols and thiols, and of course we'll be adding on additional organic families in the future. But concept mapping can be a great way to help your brain identify the interrelatedness. And this isn't just true in chemistry. I think probably you could use concept mapping in all your classes. Just start by putting like kind of the big titles, the big title pictures there, or big title concepts, and then start going off of them, and you can change colors or directions, or but start with like characteristics and then look at how they might interrelate, because the truth is, think of this as your brain. Think of these as neuron pathways that you're generating, so that alcohol also triggers knowledge about aldehydes, and aldehydes maybe triggers knowledge about ketones or alkenes, because you realize there are some similarities in the hydrogenation reaction. The more triggers and links you create in your brain, the stronger the memory pathways and the learning.